Okay, so we're going to finish these notes. The last thing that we ended with is a residual plot. There are two last values that we need to talk about. We're going to skip around a little bit, go to the bottom. First value that we need to talk about is what is called the standard deviation of the residuals. It's often denoted S, or it might be SE. E just stands for error. Okay, so what that means in general is, let's say you have your least squares regression line, so you have all of your points here, and you have a line. What S measures is S calculates all of these residuals, and S is basically the average residual. And a residual is just a measurement of error, so it's the average error. So it's the typical deviation in the y direction. One thing that can get a little unclear, SE is not the same thing as the standard deviation of y. So I want to show you on a graph something a little bit bigger what the difference is. So let's take that same graph and I'm going to put some points here. And then we have our line. Okay, standard deviation of y. That is the typical deviation from the y value to y bar. So what you would have to do is you would have to find y bar, the average of y, and then you're looking for the difference between all of those points and the average of y. So in red, that's S sub y. Like I said, SE is the residuals. That's measuring the y difference also, but this time it's to the line. So black, that is S sub E. Okay. So for the femur and humerus data, I don't know what the standard deviation was. I'm just going to tell you that SE is about 6.49. That's just what we're going to say. So the standard deviation, we need to put this in words. It is the typical deviation in the y direction from the line of best fit. So if I'm going to put that in words, I'm going to say typically humerus lengths deviate by 6.49 inches from the least squares regression line between femur length and humerus length. Here is where College Board or the AP test is going to be very picky. You have to say the word typically, and this has to be plural. So you have to indicate that you are talking about all of the points, not just one of them. So you're talking about all of the points, not just one individual. Questions on that?
Have we talked about humerus lengths instead of femur lengths?
For the interpretation?
Yeah, we were talking about
Because humerus was the y direction. So this was going back to data that we did earlier in the notes. That was our y value. So we're always looking at the residual in this case is the difference in the actual and predicted y values. Okay. Last thing that we need to interpret is something called r squared. So you've noticed when you do your regression on the calculator, it gives you r and r squared. R squared is very helpful. It is called the coefficient of determination. So you do need to use that term, or you need to know it. Sometimes I'll say interpret r squared. Sometimes I'll say interpret the coefficient of determination. So you need to know both. Again, I don't remember what the r squared value was for our data. Let's say that it was about I think it was about 0.89, if I remember. Okay, in simple terms, here's what's going on. R squared tells us the percent of time that y changes because x does. So in our case, 89% of the time, y is changing because x is changing. So our number tells us that 11% of the time, we have what we call unexplained variability. I can't write all of that, but unexplained variability. 11% of the time, y is changing for some other reason. That is the simple terms. That is not the way we actually write this. If you want to get full credit for this, you would need to say 0.89 of the variability in humerus length, and I'm just going to put in parentheses y. You don't need to write that, but I'm just telling you humerus length is y. 0.89 of the variability in humerus length can be attributed to the approximately linear relationship between x and y. But we're going to put that in context. Between femur and humerus lengths. Okay. Part of what is tough is knowing, well, I guess let me start again. We need to recognize that r squared and r are related. So if I tell you that r squared is 0.89 and I ask you what is r, of course you're going to take a square root. What you need to recognize though is that r can be positive or negative. And we talked about this, I think maybe you would look at the slope. Negative slope, r is going to be negative. Positive slope, r will be positive. R squared and s are related. Both r squared and s measure how well our line models the data. Here are some differences though. S has the same units as y. Our response variable. R squared has no units. Neither address the form of the relationship. Neither will tell us if the relationship is linear or nonlinear. For that, we would have to look at a graph. Let's say I have this data here. Last thing I want to talk about. What happens if I add a point here? If I add this red point, what is this red point going to do? Will it change R? Yeah, it's going to weaken the relationship. Will it change the slope? Slightly. Yeah, so that one would have a slight change to r and the slope. Right? It would weaken r, and the slope would become closer to 0 because our line is getting closer to horizontal. If I put a point over here, this blue one, is that going to affect r and the slope? So I'm talking about this blue point over here. Is that going to affect r and the slope? Yeah. Which one has a bigger effect, the blue point or the red? Blue. So blue will definitely strengthen r. It follows the trend, so I don't know how much it's going to change the slope, but it might make the slope a bit closer to 0 also. And what did we call that point in the warm-up?
High leverage.
A high leverage point. I don't use that terminology, but if you see that terminology again, just means does the point have an influence, a big influence.